The Newton fractal is a boundary set in the complex plane which is characterized by Newton's method applied to a fixed polynomial. It is the Julia set of the meromorphic function which is given by Newton's method. When there are no attractive cycles, it divides the complex plane into regions, each of which is associated with a root of the polynomial. In this way, the Newton fractal is similar to the Mandelbrot set. Unlike other fractals, it exhibits an intricate appearance arising from a simple description. It is relevant to numerical analysis because it shows that the Newton method can be very sensitive to its choice of start point. Many points of the complex plane are associated with one of the roots of the polynomial in the following way. The point is used as starting value for Newton's iteration, yielding a sequence of points if the sequence converges to the root. Then was an element of the region. However, for every polynomial of degree at least 2 there are points for which the Newton iteration does not converge to any root. Examples are the boundaries of the basins of attraction of the various roots. There are even polynomials for which open sets of starting points fail to converge to any root. A simple example is where some points are attracted by the cycle 0, 1, 0, 1, rather than by a root. An open set for which the iterations converge towards a given root or cycle is a fractal set for the iteration. The complementary set to the union of all these is the Julia set. The fractal sets have common boundary, namely the Julia set. Therefore, each point of the Julia set is a point of accumulation for each of the fractal sets. It is this property that causes the fractal structure of the Julia set. To plot interesting pictures, one may first choose a specified number of complex points and compute the coefficients of the polynomial. Then, for a rectangular lattice of points in, one finds the index of the corresponding root and uses this to fill in Time's raster grid by assigning to each point a color. Additionally, or alternatively, the colors may be dependent on the distance, which is defined to be the first value such that for some previously fixed small generalization of Newton fractals, a generalization of Newton's iteration is where as any complex number, the special choice corresponds to the Newton fractal. The fixed points of this map are stable when lies inside the disk of radius 1 centered at 1. When is outside this disk, the fixed points are locally unstable. However, the map still exhibits a fractal structure in the sense a Julia set. If is a polynomial of degree, then the sequence is bounded provided that is inside a disk of radius centered it. More generally, Newton's fractal is a special case of a Julia set. Newton fractal for 3 degree 3 roots, colored by root reached. Newton fractal for points in the red basins do not reach a root. Newton fractal for a 7th order polynomial, colored by root reached and shaded by rate of convergence. Newton fractal for colored by root reached, shaded by number of iterations required. Newton fractal for colored by root reached, shaded by number of iterations required. Another Newton fractal for generalized Newton fractal for the color was chosen based on the argument after 40 iterations. Generalized Newton fractal for generalized Newton fractal for generalized Newton fractal for